All right, got a lot to do still here today. Let's go over quickly this idea about using the area to find the probability. Again, keep in mind the triangular distribution here is just a model. It's not necessarily perfect in giving you a perfect answer. It's based on past data. We're imagining you have histograms that look like this. You do need the area under the triangular distribution to equal 1 in total, which you can find and you can confirm with the formula for the area of a triangle, 1/2 base times height. The base here is 2, the height is 1. So the area is going to be 1/2 times 2 times 1, which is 1. Okay? So the total area is 1. To find a probability like this, again, the idea is you've got to find the area. In this case, of this region, under the curve and above this range of values from 1.25 to 1.75. You've got to find the area of this trapezoid. It can be done in two ways. There's a formula for the area of a trapezoid. That's the base times the average of the heights. You can also split the trapezoid into a rectangular region and a triangular region and add up the areas of those two things. However, you are going to have to figure out the heights of these sides here, which means you need to think a little bit about the slope of this line. Think about it with me here. What's the rise over run? As x goes from 1 to 2, the run is 1. The rise is negative. It goes from 1 down to 0. The slope of this thing, you could write as 0 minus 1 over 1 minus 0 is negative 1. Change in y divided by change in x. It's negative 1. So, if you want to find the second coordinate of this point, which is the height of this line here, you've got to ask if x increases from 1 to 1.25, if x increases by 0.25, what happens to y? It's got to go down by 0.25 because the slope is negative 1. So the second coordinate of this point has got to be 1 minus 0.25, which is 0.75. And that's got to be the height of this side of the trapezoid. What's the height of this side? You go down, x goes up by another 0.5 to 1.75. Y has to go down by 0.5. The coordinates of this point are 1.75, 0.25. Y goes from 0.75 down to 0.25. Another way to think of it is x going backwards from 2 back to 1.75, going down by 0.25. Y would have to go up by 0.25. Any way you can figure it out is great. If you didn't follow what I said, you're going to want to think about it after class. The height of this is 0.25. The base there is 0.5. The area of that rectangle is 0.5 times 0.25. And the area of the triangle is 1/2 base times height. The base is still 0.5. The height of this triangle right here is the distance between these two numbers, which is 0.5. So the total area of the trapezoid, 0.125 plus 0.125, it looks like. Yes, double check. The area of that trapezoid is 0.25, 1/4. So that's your estimate for the probability. With continuous variables like this, where you've got a measurement like an amount of length or an amount of time, it doesn't matter whether you put less than or equal to here and here, or strict less than. It does matter when x counts something, when x is discrete, is what you say. Then the inequality type matters. But with continuous ones, if I put less than or equal to, or if I put less than, I get the same answer either way. It's still the area. Effectively, lines don't have any area, so if you sort of took those out of what you shaded, it doesn't affect the area at all. Okay? So that's something that you're going to encounter on your homework as well. You're also going to encounter problems where you've got to deal with normal distributions. Maybe you're measuring the weights of some hummingbirds. Actually, I think that's one of the examples I'm going to look at on another slide here. And I have no idea how much a hummingbird weighs. I don't know. 2 ounces? Is that too small? 1 pound is probably too big. Maybe the weight, x, of a hummingbird is normally distributed with a mean of 2 ounces and a standard deviation of 0.3 ounces. Sorry for our European listeners for not using metric, okay? And everybody else in the world, actually. 2 ounces is the mean, 0.3 ounces is the standard deviation. I'm assuming if x represents the weight of a randomly chosen hummingbird, that it's normally distributed, that these weights are going to be distributed according to a normal curve, centered on 2 and with a standard deviation of 0.3. I have no idea if that's accurate or not. It's probably normally distributed, but I have no idea about whether 2 and 0.3 are accurate. This would be 2.3 and this would be 1.7. I might now want to find the probability that a randomly chosen hummingbird has a weight between 2.1 ounces and 3 ounces. Okay, I might want to find that probability and use this notation. The probability of this event, the probability that the weight is between 2.1 and 3. How do you do it? You convert to z. It's a normal curve after all. Convert to a z-score, use the table. I want you to be able to convert to a z-score within the probability notation, which means you do all your calculations inside the parentheses. Subtract the mean, so take 2.1 and subtract 2 and divide by the standard deviation of 0.3. Do the same thing with the 3. 3 minus 2 divided by 0.3. What happens with the x? It magically morphs into a z. How? It's not magic. It's just a definition. It's just a letter. Okay? It's not really magic. It just seems like magic. There are a lot of things in math that are not really magic. They just seem like magic, although they are mathematicians. What do these equal? Well, 0.1 divided by 0.3 is 1/3. This is technically 0.3 repeating, which you'd approximate for the table's sake to be 0.33. And this is 1 divided by 0.3, same as 10/3, same as 3.3 repeating. Yeah, to use the table, approximate it like this. Go to the table. I've got it in the PowerPoint here. This is the area between 2 numbers. Remember, don't forget the table gives you areas to the left of numbers forever and ever. So I'm going to have to do a subtraction. The area to the left of 3.33, there's 3.3, here's 0.03, is right here. I know it's hard to see. You might want to look in your book. That number is 0.9996. And then the area to the left of 0.33, here's 0.33, is 0.629, I can't tell, is that a 3 or a 5? 3. I think it's a 3, yeah. 0.6293. Bad if I can't tell. So this is approximately, there's really this is all approximations. 0.9996 minus 0.6293. And that's going to be 0.3703, I think. Double check me here. I think that's right. About a 37% chance that a randomly chosen hummingbird is going to have a weight between 2.1 and 3 ounces. And again, because it's a continuous weight can vary along a continuum. It doesn't matter whether I use less than or equal to here and here or strict less than, it doesn't matter. Okay? So you want to be able to use this kind of notation. Do the z-score calculation within the probability notation. That's the standard way to do it. I want you to learn standard notation and be able to communicate that way because it is a good shorthand. All right, where are we? Let's go back to, well, let's first look at this one that says, emphasizes that random variables come in 2 varieties, discrete and continuous. I've already been talking about this without really emphasizing it, as much as I'm doing right now. X, your variable, your random variable. What is a random variable? It's a variable whose values are random, self-defining essentially. They come in 2 varieties, discrete, like counting how many heads in a certain number of flips, how many earthquakes above a given magnitude occur in Los Angeles in the coming year. You got to specify like above like a certain magnitude, because technically speaking, the Earth is always shaking a little bit. So above magnitude 5.0, for example, you can count how many there are. Those are discrete. You can count them, is effectively it. There's finitely many possibilities. It can include an arbitrarily high number of possibilities. Technically, there could be 1 million earthquakes in Los Angeles above magnitude 2.0 this year or something. I don't know. That number could be arbitrarily high, but you're still counting, so it's still discrete in that sense. It's not discrete as in hush-hush. It's discrete as in individual events that you can count, essentially. Continuous, that's where the values can be on a continuum of possibilities, like weights, heights, weights of hummingbirds, heights, time between phone calls, time between texts. Okay, those can all be measured on a continuum with an arbitrary level of accuracy. Okay, those are continuous random variables. Discrete random variables, values, probability models are described with tables, and with continuous ones, it's described by density curves. And you find probabilities either by adding the numbers on the table or finding the areas in the density curves. Our main use of random variables for this class later on, will, especially in chapter 6, will be sample statistics. And sorry this doesn't come out real nice. It looked nice in my computer. For example, the sample mean x bar, that's a sample statistic, and the sample proportion p hat will be very important random variables for us, okay? That's going to be our most important application for statistics starting in chapter 6, is we are going to be looking at sampling distributions a lot of these variables. These variables are random variables because you don't know what the value is going to be before you take the sample, and in fact, different samples produce different values. Okay, different x bars for different samples, different p hats for different samples, just like we were simulating on the spreadsheet. The sampling distributions will serve as their probability distributions. First, fixed sample size n. Okay, you have to imagine that n is fixed when you talk about a sampling distribution for one of these statistics. Okay, that's going to be our main use. In the remaining time today, we should focus on some other kinds of problems that are going to help you for the homework. I've got a lot of other slides that I don't have the time to get into. What are those slides related to? Again, don't take notes here, just glance over these slides and let me briefly mention something about them. You should download them and use them as a supplement to your reading. You're going to get more information out of the reading, but if you look at the slides, I think it will be helpful. A lot of other slides, more slides about coin flipping, and whether that's continuous or not. And we can describe a probability model for the number of heads in 4 flips. I would encourage you to think about why this works. You can list out H's and T's to help you figure out why this one works. Next time I think we'll simulate it on a spreadsheet. Can it be simulated? Of course. One way is to use random between. Okay, I'll let you think about that and we'll talk about it more next time. I'll let you think about what I might mean by that. I won't specify right now. It's going to help us model getting various number of heads based on the probability distribution. I did some results. I'll show you this again next time. It might be related to an electronic assignment you might have. Not sure if I'll give you one. We still have the test next week, so I'm unsure where we're going to be with that. We can ask new questions. Here's where I want to get to ultimately. What are the expected means and standard deviations of the simulated values? And the formulas you're seeing here are supposed to motivate the general formula. What is the general formula? That's what I'm going to get to right now. Okay, what is this crazy looking thing? We've got a random variable. It's discrete, and in fact it's got finitely many different values you can take out. x1 through xn. And corresponding probabilities, p1 through pn. You can make a little table even. Values of x and probabilities, the corresponding probabilities Imagine this table that you might make. You've got these different possibilities for x and the different corresponding probabilities. Those probabilities can't be negative and they have to add up to 1. The sum of the p's must equal 1. I'm using the sloppy notation there, not bothering with the index of summation. Turns out you can find the mean of a random variable like this with this formula. Add up the products of the values of x times the corresponding probabilities. What does this mean? What does it represent? This is supposed to represent the theoretical mean of the variable, which should be, if you're doing random sampling, should be well approximated by a sample mean, an x bar value, if you have a large enough sample size for this variable. Like if you flip a coin 4 times and count the number of heads over and over and over and over and over again, hundreds or thousands of times. Sometimes you get 0 heads, sometimes you get 1, sometimes you get 2, 3, and 4 heads. Find the sample mean, x bar, for all those. It should be close to this mean of the variable itself, which is denoted with the Greek letter, mu. X is a subscript here, you're just saying this is the mean of x. You could use parenthesis notation, by the way. You could use mu of x with the x inside parentheses. Our book uses a subscript here. It's just specifying what the variable is, that's all. The idea is to add up these products. So in your table here, you'll be doing this by hand with calculator help for the homework. You want to make another column for x times p. Multiply each x times the corresponding p. And then add up those products. The sum right there, your sloppy notation, x times p. That's going to be the thing we call the mean of x. You can also, surprise, surprise, find the standard deviation of x. Although first, so lots of other stuff here I'm skipping. Although first you find something called the variance. I should just move these up here. There we go. All right, I think that's better. A couple more formulas. The variance of x comes from this formula. What are you doing there? What does it mean? Think about what the operation is going on here. You're taking each of the x values, subtracting the mean you just found from the table, squaring those numbers, multiplying times the corresponding probabilities, and then adding them up at the end. That's called the variance of the variable. And then the standard deviation of the variable is the square root of the variance. Okay, different notations for these different things. And again, we've got the sloppy summation notation, which we kind of default to for the sake of time. That is somehow a measure of spread. In fact, if once again you did simulations of flipping a coin 4 times over and over and over again and counting the number of heads each time, getting a bunch of different 0s, 1s, 2s, 3s, and 4s, those data values are going to have a certain sample standard deviation that hopefully well approximates the population standard deviation, so to speak, the standard deviation of the variable itself. Actually, in some ways, its square does a better job of approximating the variance, which is why we bother talking about this variance thing. We're not going to get into the details of what the difference is. We want to approximate the standard deviation of the variable itself by looking at the simulated data. These numbers are theoretical. They're like populations in a sense. They're like population numbers, which is why we use Greek letters here. But we can simulate data from these distributions and see that the statistics we get from the data, the x bar and the s, hopefully closely match the mu and the sigma. There are other formulas that come up that are on these slides. There's one key equation. I want to skip over it for the moment and focus on a problem that's similar to a homework problem. Here we go. Okay, this is similar to a homework problem. For you guys, I'm not sure if it will be in the future, for future classes. Imagine a manufacturing business. Let's let X be the number of weeks required to complete the development of product specifications for the product. So you're trying to define what the product is, essentially, that you're going to make. And Y is going to be the number of weeks required to complete the design of the manufacturing process. Once you decide what specifications the product is going to have, then you've got to decide how to make it, how to produce it. There are labor costs and other kinds of costs associated with trying to do these developments in a business. Let's just pretend the cost of developing the product specifications is $7,000 a week, and the cost of designing the manufacturing process is $25,000 a week. The problem says to calculate the mean cost per week of development and design based on the following probabilities models for X and Y. These are discrete random variables here. They are numbers of weeks. We're pretending X can be 1, 2, or 3 weeks. It never takes longer than 3 weeks to decide on the product specifications. And Y, the number of weeks to complete the design of the manufacturing process is 1, 2, 3, 4, or 5 weeks. It never takes longer than 5 weeks, okay? Just for the sake of simplicity, we're making these kind of assumptions. And these are probability models. For example, the probability that X will equal 3 is 0.3. The K is an arbitrary value here, 1, 2, or 3. This notation means the probability of X equaling K. If K is 3, the probability that X equals 3 is 0.3. For Y, the probability that Y equals 4, for example, is 0.3. Okay, that's what the tables mean. I want to find what? The question says, calculate the mean cost per week of development and design together. Find the mean, mu, of these costs. X is the number of weeks for the product specification at a cost of $7,000 per week. Therefore, 7,000x represents the cost variable, essentially, for product specification. So if X is the number of weeks it takes you, and it costs you $7,000 a week, 7,000 times the number of weeks will be your cost in dollars for specifying the product. That's part of the cost. You also have a cost from the design of the manufacturing process. That's $25,000 a week. If you take 25,000 times Y, that's going to be the cost of the design of the manufacturing process. Y is the number of weeks it takes you. 25,000 is the cost per week. Adding these two costs together gives you the total cost, the combined cost of development and design. Now there's a fact, a fundamental fact to know, that's on the spreadsheet, back right here. I'm going to use this formula essentially, that tells you how to find the mean of a combined variable like this. AX plus BY, where A and B are constants. That's what I have here. The A is 7,000 and the B is 25,000. I'm not explaining the meaning of this formula in terms of why it's true. For the sake of time, we're just using it today. To use that, you have to take 7,000 times the mean of X plus 25,000 times the mean of Y. That's what this formula would say in this example. Again, your problem is pretty similar to this. Not exactly the same. I changed the numbers a little bit. But it's pretty similar. But that begs the question, then, if you trust this formula, and again, I'm not explaining the formula. No time to. If you trust this, now you have to figure out what these numbers are. And you got to get those from the formulas. Let's get it quick from a spreadsheet, and that'll be the last thing we do today. I'll share this with you. I've got a product development spreadsheet. It's a modified version of exercise 4.59. You will be doing 4.59 itself, which means your numbers will be a little different. What I want to do is I want to first find the means. Well, we are focused just on means, actually, not the standard deviations. I want to make a column for the x values times the corresponding probabilities. And I want to add up those products. That'll find means. That's the formula that I showed you for mu x with the summation. I made the table on the board, wrote down the idea. Multiply each possible x value times the corresponding probability. Add those up. Let me put the sum down here. I went D6 through D11 because I'm going to do the same thing over here. 2.1 is the mean number of weeks for deciding the product specification based on past data when you imagine doing this process over and over and over again. That's what the theoretical mean is. What about for Y, the design and manufacturing process? You do the same kind of thing. And its mean is 2.95 weeks. Therefore, your final answer for the mean total cost of product specification and design put together would be 7,000 times 2.1 plus 25,000 times 2.95, whatever that turns out to be. Okay, for the sake of time, I won't bother finishing it. What would it be approximately? This would be approximately 14,000. This would be close to 75,000. It's going to be close to $90,000. Is your total mean or expected cost for this process of product specification and manufacturing design. Okay? See you next time.